your program advisor and ask them if P and Z is okay with your program. And then obviously, if that's what you're opt for, then you're going to be notified sometime this week, I'm told, where you can make the decision. But in the meantime, yes, you can still get a regular ABC grade, and that's if that's what you want. Um, then whatever grade you want, at some point in time, I want you to send me an email. Don't have to do it now. Wait till you get all the facts and how it affects your program, and then send me an email to your decision. Okay. Now that doesn't stop us from continuing the semester. We still have to, you still have to, do the homework, the quizzes, and so forth. Which reminds me, today exam number 2 will shut off at 11:59 today. So if you haven't done it, uh, make sure you give yourself plenty of time. There's 22 questions. You're given 75 minutes to complete it. On average, people have been taking about an hour. Uh, Make sure you have uh, the access to the spreadsheet, and that's not the spreadsheet. My apologies. The periodic table. There's in both the periodic table and the shapes table. Obviously, there's a lot of information there that you can utilize. Okay. All right. So, any questions about the new grading system right now? That's something I can answer very quickly. But if you have more extensive questions, feel free to shoot me an email. Couple of things, couple of reminders. I do have Zoom um, office hours here Monday and Wednesday, 1 to 2, and on Saturday, noon to 2 o'clock. And those are flexible. I can spend more time as needed. So far, no one's come by and knocked on the door to do office hours, but I am available for you. Second thing, there is homework on the course website. Some classes did the long handout homework. Um, that's an additional resource for you. The key has been posted for homework set number 2. I would take a look at that. Also, old exams, the keys there, take a look at that. And the worksheets, because all those examples, uh, if you use them as a resource, you'll find the exams will be very similar. The exam questions will be very similar to what you see there. So it's an additional source. Now, if you haven't taken the exam or you have already, and you type it's multiple choice, but there are some short input your answer. If you mistyped it, or the answer is correct, but Canvas said you're wrong, shoot me an email. I'll be more than happy to go in the exam, take a look at it, and if your answer warrants credit, I would definitely give you your points back. So, okay, don't hesitate to do that. Yeah. With respect to email, please use Canvas email. That is the official method of communication between students. Also, I mentioned this again before, that Canvas email, when you send me that, it comes right to my phone. I can answer it fairly fast. My other email, my school email, the GCC-Az.edu, sometimes that's delayed for some reason. I don't know. So if you send an email through there, I may not answer it as quickly because sometimes I don't get it till like a day or 2 later. So keep communication through Canvas email. All right. Well, I'll tell you what, today's chapter, you can see here, it's actually 12 pages, very short, and it probably won't take the whole time. So after this slide presentation, I'll hang around. If you have any questions, you can bring them in and we can talk about them. Otherwise, we'll go through it and we're done. And I'll see you on Thursday. Chapter 12 also is fairly short. 13 and 14 are a little bit longer. 15 is a short one. But 13 and 14, we'll probably spend a lot more time on those chapters than we will on this one and 12. Okay. All right. So let us begin. Thermodynamics. That's what this chapter is about. Now, this chapter is a topic that we're going to talk about. We're just giving you the tip of the iceberg. Thermodynamics, basically, if we look at the term thermal meaning heat, which is related to energy, and dynamics meaning the movement and things moving. So we're talking about how energy affects, we're going to be talking about how energy affects reactions and what is necessary for certain things to occur. It's not always a simple matter of you just putting A and B together and, magically you end up with whatever product you're getting. There's a lot of factors involved to ensure that products are obtained. Okay, so come on. We have what's called a collision theory, which basically is telling us that in order for reactants to form a product, they must collide and come together. And when they do come together, they gotta have a couple of things. They're gonna have the correct orientation relative to each other, and they gotta have sufficient energy to produce product. And if we look at the slide here, we have two reactants, two completely different reactants that are coming together with the right orientation, okay, to eventually produce two new products, okay? Now, to get from point A to point B, they actually go through this intermediate that I circle here in the center. Now, that has a specific name. That is what we call a transition state, and there'll be more on that in other slides are coming up. That is the point here that you can see that two things are happening. We're breaking bonds and we are creating new bonds simultaneously. The correct orientation must occur. The correct amount of energy or minimum energy must occur for this process to happen, okay, to form products. So we got bond breakage and bond formation. Transition state, that's the intermediate. Now, we're going to have successful collision between reactants before anything of this happens. Any product occurs. Now, we can do that by, what we can do is we can find ways to increase the number of collisions. There's a couple of ways we can do that. Obviously, if you think about it, if I have 10 molecules reacting together versus 1,000,000 molecules reacting together, well, the chances are much better that with 1,000,000 molecules as compared to only 10 molecules coming together. So that's one thing we can do. We can increase the concentration to make sure that we get sufficient collisions to occur to give us a product, okay? We have to have enough energy for once, even though we have a lot of products, a lot of reactants together, if you don't have enough of specific energy, which we call activation energy, and is denoted by the letter capital E with a subscript A, we call that the energy of activation or activation energy, either way, okay? That is the minimum amount of energy for a reaction to have to become products, okay? Energy of activation. Now, in the previous slide, you saw how the molecules, reactants, had a specific orientation. Again, you're going to have numerous molecules coming together, but if they don't have the correct orientation, you're not going to have a product. Okay, so they have to be orientated. They have to be orientated correctly. They have to be have enough energy of activation. So this one thing I mentioned, we can increase the concentration. Okay, somebody got one more to come in. 1 second. All right. Now, if you recall, in the acid-base chapter, we introduced these brackets. Okay. Those brackets here represent concentration. So if we increase the concentration of the reactant, we're going to have more reactants, hence have more collisions. Okay. One way to give it energy, sufficient amount of energy to overcome that energy of activation barrier, is to heat it up. If we simply heat up a reactant, boom, we make the molecules go faster. Molecules go faster, now they increase the probability of them coming together with the right orientation to form whatever product it's going to make. Okay, we got one more coming in. Okay, now increase the temperature. However, that doesn't always happen. Hell, even increasing the temperature sometimes can cause reactants to break down. And so, you know, you got to be careful. Normally, as a general rule of thumb, for every 10 degrees of temperature that you increase a reaction, you double the rate that the reactions occur. Okay? We can add what is called the catalyst. Now, we got catalysts all around us. Your body is loaded with catalysts. And what all catalysts do is they lower that energy of activation for a reaction so that reaction can proceed. They're not directly involved with the reaction other than lowering the energy of activation. Once they're done, catalyst goes on and does the same thing for another set of reactants. Okay? Like I said, where your body is loaded with catalysts, enzymes, and so forth, that if we did not have in us, life as we know it wouldn't exist, because the reactions of breaking down molecules wouldn't occur and you wouldn't have energy. In fact, you're driving around with a catalyst. Your catalytic converter has a catalyst, very expensive catalyst, to deal with the exhaust of your vehicle. Okay? So, summarize the energy of activation. That is the minimum amount of energy needed for reactants to react. Okay. We also have what are called equilibrium reactions. We kind of introduced this a little bit in chapter 11 with acids and bases when we were talking about weak electrolytes and weak bases. And they were weak because in that case, they did not dissociate 100%. And so we have a double arrow here that basically just says that the reactants A and B going to C and D, that rate of reaction is just as fast as going the reverse direction. And hence we have an equilibrium reaction, okay? Classic example of this was if we were in classroom, I would pull up my soda pop and shake it. And you know that the bottle would fill up with pressure. And if you uncapped it, obviously you get a big mess. But if I leave it capped and I set it aside, eventually the gases that have been emitted will go back in solution and we'll go back to another state of equilibrium. Okay. So equilibrium reaction. Now, we have diagrams. Scientists, we like diagrams. We like charts to describe things. And in the upper right, there is a diagram that would demonstrate this, what we call energy profile. Basically, it is a plot of energy which goes in the x-axis, that is the horizontal axis, versus the reaction itself, which is the horizontal, how the reaction proceeds from reactants to products, okay? Now there's special, when we plot that graph, we have special areas that we need to be aware of. Okay, for example, the transition state, that's labeled on that graph in the upper right corner as TS. That is that intermediate state between reactant and products that everybody must, all reactants go through, okay? The delta H, delta meaning the change of energy, That is the change of heat energy, or the heat of the reaction. That is denoted, if you look at that graph on the right-hand side, the energy difference of where the reactants are versus where the products end up. The axis, the x-axis, which is this axis, sorry about that, right here, those are energy units. Right now, they're just arbitrary energy units, okay? So you can see from the graph that in that example, the energy amount of the products is much lower than the energy amount of the reactants. That difference is what we call delta H, the change of heat energy. And that's basically the energy of reactants, okay, minus the energy of the products. Now, if a reaction gets cold, you may have done this before. You get a cold pack, you go to the pharmacy and buy a cold pack, and you smack the container in the bag, and it gets cold, okay? That is what we call an endothermic reaction, because it's absorbing energy from the environment. And so it gets cold, the area gets cold. So notice that here in this reaction, that heat or energy is a reactant, okay? With respect to a reaction that gives off heat, okay, we call that exothermic. Energy is given up. Again, at the pharmacy, you can buy hot packs that you get and you smack them. Reaction occurs with the chemicals in that pack, and it gives off heat. In this scenario, in this scenario, heat or energy is a reactant, product, excuse me, okay? And it gives off heat, it gets warm. Now, here is that diagram a little bit bigger. And so what we have here is the energy of the reactants. And then if we look at the products, I can draw a line all the way to the axis, okay? Remember, this is energy axis here. We can arbitrarily say, okay, this is 10 units of energy, and this over here that I'm drawing is 20 units of energy, okay? Thing to notice here mathematically, that delta H is the energy difference between products minus reactants. And so in this example, the energy of the products is 10 energy units. The energy of the reactants is 20. So 10 minus 20 is negative 20 energy units. That's what delta H. Having a negative value tells you that this is an exothermic reaction. Now you can look at this mathematically and do what I just did here by putting arbitrary numbers on the energy axis, or you can see that the products are lower in energy than the reactants. Therefore, I end up with an exothermic reaction. Therefore, I end up with a negative value for delta H, okay? The converse will be true. That is, the opposite would be true if you go over here. Look at this one here. Okay, we have the reactants and the products. Again, we can put arbitrary numbers here and say, call this 10 units for the reactants, and arbitrarily say, I don't know, 20 units for the products, energy-wise, coming over here across. Okay, delta H, products minus reactants, 20 minus 10, positive 10 units. So in this example, this is an example of a endothermic reaction because our delta H ends up as positive. Well, the point of this, all this is one, be able to look at a diagram and just by looking and determine, is that exothermic or endothermic, okay? Second of all, be able to identify the transition state, which is on top of the hill there. Okay, that is that state where you got a mixture of product and reactant. Be able to identify delta H, which is the difference of energy between products and reactants. Okay, and then identify energy of activation, and that is that energy difference between where the transition state is minus where the reactants began. So that's the energy of activation right there. That's how much energy the reaction would need in order to become product. Okay. Looking at this one here, what would you think if this was endothermic? Is delta H positive or negative? Okay. Well, looking again at where the reactants, where the products are compared to the reactants, that difference of energy from here to here would give us a positive number. Therefore, this guy would have, this example would have a positive delta H in this reaction. So then it would be endothermic. Okay. Here are the two graphs that are side by side. You can see in the top one, hold on a second. You can see in the top one that if I needed to determine the top one, who would like to volunteer and tell me, would that be a negative delta H or a positive delta H? Or the top one, which we're going to call A and B. What could I say about A? Who would like to volunteer? You can chat it or you can unmute yourself. For volunteers? Okay, we got an Excel. Dylan says Excel. That is correct, Dylan. Okay, because we can see here that the products are in much lower energy state than the reactants. So we would have an endothermic reaction here. Okay, and then the converse of the opposite would be true for the B. B, the products are in much higher energy state value-wise compared to the reactants. So the difference between products versus reactants, that difference will give us a positive number. So that would be an example of a positive delta H, therefore endothermic reaction, and A would be a negative delta H, therefore an exothermic reaction. Okay. Now, catalysts, as I mentioned in the beginning, and guys, we're almost done with this chapter. I told you it was short. In fact, this is probably the last slide. All the catalyst does is lower the energy of activation. Normally, the energy of activation is somewhere right there. That would be EA, okay, in the normal position. But with a catalyst, notice what happens to it. The energy of activation gets dropped much lower. And so that reaction that maybe would require, 80, 90 degrees, for example, to react, with a catalyst, that reaction occurs maybe at room temperature because it doesn't require that much energy to get it over to products. And the point again with respect to catalysts is they just lower the energy of activation, but they themselves do not get involved with the reactants directly. They don't become part of the products. They're released and then go on and repeat the process. Okay, and so with all being said, guess what? Chapter 11 is done. So be familiar with looking at energy profile of a reaction okay? And be able to identify those 3 or 5. Oh, back up. Hold on 1 second. People coming in late are going to be disappointed. We're almost done. I did mention this is short. Be able to identify where the reactants are, where the transition state is, where the energy of activation is, where delta H of the reaction is, okay? And be able to identify whether it's exothermic or endothermic, and whether delta H would be a positive value or a negative value. I think if you got those points and you can do that, this particular chapter hopefully should not be a challenge. And also a catalyst, basically what the catalyst does is lower the energy of activation, but in itself does not get involved with the reaction, other than playing with the energy of activation. So that's the end of chapter 11. Chapter 12, which we'll do on Thursday, is probably just as short. However, it may take a little more time because there are some calculations involved there. But other than that, chapter 11's done. I will reserve the rest of the time for any questions you have concerning, whatever chapters or the exam or anything of that sort. So if you're happy with where you're at now, feel free to log out, and I will see you on Thursday, and we'll hit with chapter 12, and I will have office hours tomorrow between 1 and 2 here on Zoom. So you guys take care and be safe out there. Okay?
Hi, Dr. Fred. This is Rhiannon.
Yes, Rhiannon. How can I help you?
So I haven't been able to get to class recently. I'm terribly sorry about that. There's just been a lot going on.
Sure.
Where can I find the recordings?
Okay, the recordings, have you had a chance to check the email I sent this today?
I did. I didn't know if it had a link or...
Yes, at the end of the email, there is a link to the recordings. In fact, let me see if I can transfer that. Oh, no. Okay, I can't transfer that. Let me see if I can get to my link here real quick, and I can send it in chat.
Okay, that would be awesome. Thank you so much. And again, I'm sorry for not being able to make it recently.
Hey, no problem. A lot of people are going through a lot of stuff. We all understand that. And we just got to do the best that we can do. Okay.
Thank you so much.
Yeah, and just keep up with the assignments, and let's copy this. Keep up with the assignments and the homework and all that. Okay. Let me see. Let me send chat here. I think this might work. Let's find out. Okay. You see it there?
I do. And this has all of them, right?
Yes, all of them except today's. Today's I'll probably get them up there later today because they got to be converted.
Mm-hmm.
And once they're converted, then YouTube's got to do their conversion. So maybe late evening. But they're all labeled the day and what chapter we talked about.
Wonderful. Thank you so much.
Not a problem.